Hello, everyone. Let's get started. I am Grigory Demchenko, and I am working for Yandex for more than 3 years. And today I would like to talk about Asynchrony and Coroutines. I guess it's a very interesting topic because it likes compiler and execution hacking. You can implement unusual stuff that cannot be implemented using common approaches. Here is a list of topics that I would like to discuss. First of all, I would like to discuss different approaches related to simple server functionalities. We are going to discuss different advantages and drawbacks of different approaches and formulate our dreams about how it should be. Secondly, I'll introduce coroutines and show how they can be used together with asynchronous programming. I'll consider interaction with schedulers. They allow to further increase your readability and simplification of your code. Multithreaded applications usually use shared data to access between threads and to cooperate between threads. And we consider synchronization aspects and non-obvious solutions. And finally, I'll summarize my presentation. Okay, let's consider a simple server. And the task is to utilize as much CPU as we have. And we would like to accept new client connections and handle them. The first obvious solution is to create on each client to create new thread. And here you can use the code that represents that idea. First line is to create acceptor that allows us to accept new connections. Then in infinite loop, I accept client incoming requests and start new thread. For example, here I use struct for that purpose. And I obtain socket to manipulate the data. And then I read my data from the socket, obtaining a request, and then I handle that request, obtaining a response, and then I write that response into the socket, and client may receive that data. It looks very simple, but it contains significant drawback, because here you can see 3 blocking calls: on accept, on read, and when I write the data, right? And I would like to avoid blocking calls because it's a waste of CPU resources. Instead of doing useful work, most time I'm waiting for I/O events, and I would like to avoid that. Thus, I would like to do it in another way. I would like to use asynchronous server. And the idea here is to execute a callback that is going to be executed on a completion. When operation completes, the callback is executed, and I can continue my operations. Here you can see the code that represents that idea. First of all, I create acceptor as before, and then I invoke onAccept method to accept new connection. And inside callback, it's going to be invoked on completion. I do onRead operation. And inside the onRead, I obtain a request, handle it, and obtain a response, and then I invoke onWrite to finalize my handling. This code contains 3 asynchronous calls. They don't block my execution, and it's more careful resource utilization. But you know, it's not so simple as it was before, because it's complicated because I need to wrap my completions using a callbacks, and it's like a diagonal programming because each asynchronous call allows you to use a lambda, and each lambda adds more and more spaces into your code. But actually, it's not a real code. It's a simplified version because that code doesn't contain appropriate error handling, it doesn't contain a loop, the real code is look like the following. You don't need to look through that code, it's just to illustrate the complexity of the real server, and you can compare with a simplified version. So it looks pretty complex, and I would like to reduce the complexity. Okay, let's discuss the advantages and disadvantages of the asynchronous server. First of all, we have a better performance because currently we don't block our threads. We are performing our necessary stuff, and we carefully utilize our CPU resources. And because callbacks can be invoked at any thread, it provides automatic concurrency and parallel execution. But there is the only nasty drawback, and it's a complexity, and the sources of that complexity in the following. First of all, the code complexity is growing faster than the original complexity of the task in a non-linear way. And secondly, you need to have an explicit context manipulation, right? And you have also strange and a little bit complicated error handling because at any time you have to deal with error because callback can return errors at any time, and you need to do appropriate cleanup procedure. And it relates to the another complexity related to object's lifetime. The common approach is to use a reference count approach, like using a shared PTR or enable shared from this, and you have to use it explicitly on any call, on any callback. Another aspect related to debugging, because, for example, you have a stack trace, but you don't understand the history from a stack trace because you have just invocation of your callback, and you have to extract necessary data based on a context, and sometimes it's very tricky and complicated thing. Thus, the asynchronous approach tends to be error-prone. It might break your production under a high load due to unpredictable and unexpected asynchronous paths in your overcomplicated logic. And what would I like to have? I would like to combine both synchronous and asynchronous approaches and eliminate the drawbacks, specifically to take effectiveness from asynchronous approach and to take simplicity from asynchronous one. And how can this be achieved? And the answer is use coroutines. Obvious, right? Let me briefly introduce the coroutines. So everyone, I guess, knows that routine means it's just ordinary function or method, and it means that on return you have completed all routine actions, while coroutine means a partial action completion on invocation, right? Routine is a special case of coroutine because coroutine can be suspended at any time, and you can then resume it. And those points, you can have several points of suspension. And here is a short list of well-known coroutine examples. Python generators are coroutines, and Async await C++ proposal also contains coroutines. Actually, there are 3 proposals related to coroutines. Stackful, there are stackful and stackless proposals. I'm going to talk about stackful coroutines. It's a method of saving of context execution, and it provides more powerful and it provides more flexibility for your code. But we have a problem because coroutines are not part of the language still, and we need to use low-level manipulations to save our context, to switch to another context, and it depends on a platform, on a compiler, on an architecture. Fortunately, we have a solution. It's a boost.context library, and it's very effective because it contains a very simple assembler instructions. It provides a wide range of platforms and architectures, and from the user perspective, it looks like a cross-platform library. And you don't need to use heavyweight constructions like OS fibers and such that stuff. Just use a boost context because it's a very low level and very effective library. Okay, let's briefly discuss the content of boost context. It consists of two functions: make f context that creates our context, and jump f context that allows us to switch to another context. And particular usage is the following. The first step, we need to allocate stack memory. Then I need to create a context by invoking make f context function. Here I should specify stack parameters and coroutine callback to be executed. It can be any callback that I want. Then I would like to start or resume my coroutine. For that purpose, I invoke jump f context, right? And here I specify the caller context to be saved here and our created coroutine context and a pointer to transfer data to the coroutine. And to return or suspend from coroutine, I invoke jump f context, but with swapped context parameters. You see, looks pretty the same. And now, using this technique, let's consider the implementation of coroutine. Here I have a corofun. It's a function. It's an ordinary function. It doesn't contain any specific types, like futures, whatever. It doesn't contain special keywords. It's just an ordinary function. And inside that function, at any time, I can invoke yield to suspend my execution. And here you can see a usage. First of all, I create an instance of my coroutine by using coro class, and I immediately start that coroutine. Then coroutine is suspended, and I resume it later. And log output represents the sequence of operations. You can see that I start, then suspend, and that stuff. And now I have a coroutine, and I would like to transfer my code and convert my asynchronous invocation into synchronous invocation. As you can see, the synchronous invocation is a real synchronous form, and you don't need to specify callback here. And we can use the following implementation. In the first step, I obtain the reference to the current coroutine, and then I invoke my asynchronous function. And in callback, I just resume my coroutine. And the only thing I needed is to invoke yield to suspend my coroutine. So when asynchronous operation completes, my coroutine through the callback will be resumed automatically. Let's consider the sequence diagram and the sequence of operations. Here I have thread that it can be like std thread, whatever you want, and here the coro implementation based on boost context library, and I would like to implement async write function, and network allows me to handle that operation in an asynchronous way. In the first step, I start my coroutine, and then I invoke my asynchronous operation, and then I suspend my coroutine invoking yield function. Then I wait for completion. And when async write is completed, I invoke resume and continue my execution. Pretty straightforward. And this procedure doesn't block the thread because between yield and completion, we can handle actions of other coroutines or other events, right? And it looks like asynchronous invocation, but actually it's not. But here is a problem, race condition, because in a multi-threaded environment, we have not the only thread, but we have a set of threads. And here I start coroutine as before and invoke async operation. And due to asynchronous nature of the thread on operation scheduling, we might have a situation when completion is invoked inside thread number 2. And in that case, the coroutine will be resumed in thread number 2, but before suspension in thread number 1. And that, of course, is not our intention because it breaks our application, actually, right? And we need to take step back to resolve it. There are a set of solutions that you can apply. First is to use a well-known approach. The idea is to obtain and release logs on resume and yield operations. Second approach is to use boost ASIO strand. I'll talk about strands a little bit later. And I prefer using the defer approach, and let's consider it in detail. The defer approach is very simple. It delays asynchronous operation invocation. And here you can see the interface of the defer operation. It accepts handler that is going to be invoked outside the coroutine. And that handler must contain an asynchronous operation. Let's consider a sequence of operations in detail. We have thread, our coroutine, and network as before. I start my coroutine, and then I would like to invoke asynchronous operation, but I invoke it inside defer method. After that, I immediately suspend my coroutine and invoke saved async write operation. It's saved inside defer method. And on completion, I resume, and you see that this approach guarantees that we don't obtain the mentioned race condition because we invoke our asynchronous operation outside the coroutine. And this solution is lightweight because it doesn't involve synchronization mechanisms. Okay, now we can rewrite our incorrect version that contains race condition into using a defer approach. And the first step, I obtain reference to the current coroutine as before, and then I invoke defer method. Inside that, I specify my asynchronous call, my asynchronous function, async, and inside async call, I just resume my coroutine. And defer automatically suspends my coroutine and do necessary stuff. And on completion, my coroutine is resumed and continues my operations. But to completely isolate coroutines from our logic, I would like to introduce a new, more powerful function, defer proceed. This function accepts the callback that accepts the proceed handler as an input parameter. And invocation of that handler resumes the suspended coroutine. This trick allows me to abstract from the knowledge related to the coroutines. Pretty straightforward, and you can apply this method for all asynchronous invocation. Thus, I can use this approach and can rewrite my server using a synchronous form. Here you can see that I do the same stuff as it was before related to a synchronous server. And at the same time, it doesn't block the thread because coroutines are suspended and resumed, and during suspension and resume phase, you can handle another actions. And thus, we have achieved our goal to have an efficient but simple implementation. Okay, now it's time to talk about schedulers. First of all, let me introduce a simple interface. It contains the only method to schedule our handlers. And the task is to execute handlers using, for example, thread pool or whatever you want. It doesn't know about coroutines, it doesn't know about handler internals, it's just a scheduler. And it's a generic approach. It allows me to simplify my logic and to easily extend it at any directions. And the first scheduler is a thread pool. Here you can see the prototype, and in constructor I create the specified number of threads, and schedule method invoke IOService post method, and boost A0 IOService allows me to utilize create a thread and schedule my operations in those threads. And and as I said before, it allows scheduling handlers at any created threads, right? This simple implementation. And now I would like to combine and to create Coroutine Wrapper that combines scheduler and our Coro implementation. Private section contains the following definitions. It contains the pointer to the scheduler, coroutine instance, and defer handler that should be invoked outside our coroutines. And defer implementation contains two simple steps. The first step is to save our defer handler for later usage and then suspend our coroutine. Defer method is invoked inside coroutines. And proceed method just schedules the Coro resume, the resuming our coroutine. And it schedules two steps function, two steps lambda. The first step is to resume our coroutine, and the second step is to invoke defer handler. Defer handler, as I mentioned before, contains our asynchronous invocation. Okay, now using this wrapper, I can introduce teleportation. Here you can see a Go function. Go function creates new coroutine and executes it in specified scheduler as a second parameter. Scheduler is a thread pool number 1. And now I perform some actions, and I would like to switch to another scheduler, for example, second thread pool. For that purpose, I invoke teleport function, and it allows me to switch to another scheduler. And all further actions will be invoked using a second thread pool. Let's consider the implementation of that function. It's very simple. First of all, we need to assign scheduler to our specified scheduler. And I invoke defer, and here I invoke proceed to resume my execution, to resume my coroutine execution. Because I set scheduler to a new scheduler, it will schedule using a new scheduler, using a specified scheduler. And it provides you automatically switching from one thread to another. And let's consider the sequence of operations. Here you can see two schedulers, number 1 and number 2, and coroutine. And the first time we are inside scheduler number 1, and we would like to switch from the first scheduler to the second scheduler. For that purpose, I invoke teleport function, and inside that, I invoke defer that invokes yield function to suspend my coroutine. That inside defer handler, it invokes proceed, and proceed invoke schedule using a scheduler number 2, and it's resumed using a scheduler number 2, and now coroutine is executed in another scheduler. Thus, the coroutine may teleport from any thread to any thread as you wish using this scheme. And teleport is a half of the success. Let me introduce bidirectional teleportation known as portal. Portal uses constructor and destructor, and inside the constructor, I teleport to destination to the destination scheduler, and in the destructor, I teleport back to the original scheduler. And RAI approach guarantees teleportation of the original context to the original context in any situations. Let's consider typical portal usage. Let's assume that we have a network that allows us to handle different network events, and all those actions must be executed inside the network pool. And now I would like to isolate two types of operations. One type is related to a CPU-intensive work like data processing, and I would like to use command pool for that purpose. And network operations must be executed using a network pool. Thus, I specified two different thread pools. Then I would like to attach network to a network pool. It means that every network operations are going to be invoked using a network pool. And then I create a new coroutine and schedule it using a command pool. Then I do some data processing tasks, and then I would like to handle network events, for example, to receive additional data to be processed. Thus, I invoke portal function and specify network class here. Portal function returns a proxy object. Proxy object contains a portal, and inside the constructor, it teleports to a network pool, to attached network pool. And in a destructor, it returns back to the original scheduler command pool, right? Thus, this line guarantees that handle network events will be invoked using a network pool. And it's a non-blocking call because it allows to other coroutines perform some data processing. Thus, you can see that at the place of portal invocation, I don't need to know about a particular scheduler. I just use it transparently to the user. Thus, the portal is an abstraction around execution environment. Now let's talk and let's consider synchronization aspects and coroutine interactions. For that purpose, I would like to introduce another pattern alone. Usually, shared objects require synchronized access, and the common way is using std mutex. But alone allows me to do it in a very different way. Alone is a scheduler, and it implements a schedule method. And here I use a strand and strand.post to post a given handler. And the idea here that strand guarantees non-concurrent handler execution. Thus, it provides serializable access to our data. And it prevents us from race conditions. Thus, alone is a non-blocking, deadlock-free synchronization because it's a non-blocking because we use a coroutine underneath, and that can be suspended and resumed without blocking the thread execution. And it's a deadlock-free because you cannot schedule your coroutine using two different schedulers. The only one is available at any time. Thus, a deadlock is impossible in that scheme. And it's a synchronization because it serializes access using for the global objects, for example. And to summarize our knowledge, let's consider integral example. Suppose that we cache the necessary data by using memory and disk caches. For simplicity, I use the same interface. It contains a get method to obtain data from a cache, and it uses a set method to put data into a cache. And if we don't have a data inside our caches, we have to go to a network and perform request using a network. And I would like to isolate three types of operations. First of all, data processing tasks should be invoked using a command pool. Disk operations should be invoked using a disk pool because those operations are blocking operations, and I would like to avoid blocking our tasks related to data processing. And I would like to isolate network operations using network pool, right? And I would like to serialize access to our memory and to synchronize the access. For that purpose, I create a lone scheduler. And final stage of initialization is to attach portal to corresponding scheduler. Then I attach disk cache to a disk pool, mem cache to a mem alone, and network to a network pool. Okay, it's an initialization phase, and now the task is to obtain our value. We have a key, and the first step is to check the value using a mem cache. For that purpose, I invoke portal function and try to obtain key here. If we have a result, I immediately return it back to the client. If mem cache doesn't contain a value, I try to use a disk cache to obtain that value. If disk cache doesn't contain a value, I have to use a network to perform request. For that purpose, I invoke portal, and it automatically switches to a network pool here. And I obtain a value. And now I would like to put that obtained value into my caches because those caches don't contain a value. But I would like to do it in an asynchronous way to avoid waiting the client and the caller. Thus, I do it in parallel. I return and store data into caches. So it's a very simple approach. And I would like to emphasize portal features. First of all, portals are exception-friendly mechanism because it contains RAII technique and the coroutine low-level context switches allows to freeze the thrown exceptions without additional efforts automatically. You don't need to deal with exception PTR. This low-level switching provides that functionality for you freely. And it allows us to easily combine different parts or modules without explicit scheduling and synchronization. Thus, it's abstraction around execution. And now let's finalize the presentation. And to finalize, I would like to prove the simple theorem. This theorem states that any asynchronous task can be implemented using coroutines, and we can transform into asynchronous form our asynchronous invocation. Let's consider the simplest case when and assume that there is no code after asynchronous invocation. Using the transformation discussed before, I can convert it into a Synca function and call back execution. So I invoke Synca, right? Then wait for completion here asynchronously, and then I need to invoke callback. And it has, semantically, it has the same meaning. Now let's consider the most generic case when we have the code after asynchronous operation. To transform that case, I do the following trick. I execute an asynchronous operation inside the newly created coroutine. It looks like I introduce more asynchrony, but actually I don't, because I cannot make asynchronous call more asynchronous, right? It's an identical transformation. And finally, I reuse the transformation from the first step and replace the asynchronous call inside the coroutine into a Synca invocation. And because now we don't have any statements after the asynchronous code. Thus, any asynchronous invocations can be transformed by using this technique by using the coroutines. So, QED. And let's summarize my presentation. Using this theorem, we can transform any asynchronous invocation to a synchronous code, obtaining simplicity. And the coroutine approach efficiently uses threads, avoiding blocking calls. A lone scheduler allows us to utilize non-blocking deadlock-free synchronization. And portals abstract schedulers and are completely transparent to the user. You don't need to know about particular scheduler at the time of invocation. I've introduced new useful and interesting patterns like teleport, portal, alone, as I mentioned before. And it's very cool because it provides lower-level execution hacking by using high-level abstractions without additional support from compilers by now. You don't need to use special keywords. You don't need to use special types. You can use it right now in a very effective manner. My code is freely available here. And thank you very much for attention. Feel free to ask any question.
Excuse me, I have a question. So did I understand it correctly? Every time you use a portal, the whole context of this function of the subroutine is copied. Can it be expensive, or like, can you argue on that, or maybe I just misunderstood something? What if the context is large, for instance?
Context, we save our context, meaning that we store, for example, registers using special structures, but we don't copy those structures from one thread to another. We have a reference to the structures, and those those data are placed into a heap. So you just switch to another thread, and that thread uses those references, and you don't need to copy any context in that case. The only thing you need is to extract saved registers and move it from memory to actual registers. It's a context switching technique. Okay.
Hi. I don't remember seeing anything about return values. How does it interact with state future or something like that?
I don't use futures at my code because, from my understanding, futures complicate the overall code because you need to deal. If you take a future, you need to have a promise and you need to have a synchronization mechanism. If you consider, for example, current implementation of async functionality in C++11, it contains future, promise, shared PTR, mutex, condition variable inside that, and you need to have an explicit synchronization mechanism for that, and it's a very heavyweight constructions. And thus, I would like to avoid using futures, and as you see here, let me show you this. As you see, portal allows me to return a value, right? For example, I perform a request or I get a value from a cache and it returns a result, right? But I don't need to use the futures explicitly here. It performs automatically for me. The only thing I need is to switch from one context to another, and I can use a switching technique to provide asynchronization mechanisms. For example, memcache uses synchronization. It doesn't reschedule it using another thread pool. It uses the same thread pool, but it synchronizes the access to the memcache instance. So in that approach, you don't need to use the futures at all.
Okay, thanks.
Okay.
did I understand it correctly that you use some technique to switch the context of the thread with some assembler magic or something to another place? So what about exceptions? They do the stack unwinding if an exception is thrown. How does it interfere with the code that switches the thread context to another set of registers? And
Yeah, as I said before, it's switching is exception friendly because it manipulates on a very low level, right? And it allows to freeze the thrown exception using this technique. And because exception throwing is just an ordinary assembler instructions. It's not like, it doesn't involve the operating systems, right? It's a user level technique. And any user level operation can be suspended using context switching approach, using boost context library. Thus, it's completely transparent to exceptions. And there is no exceptions for exceptions from the context point of view.
you mean there's some magic in this code that switches context that also handles stack unwinding for exceptions?
Yeah.
It's not covered here in your...
Yeah.
Okay.
Also, boost context actually contains some steps to switch data, internal data, to be able to deal with an exceptions. So it's inside boost context library.
Okay, thank you.
Can you offer any performance numbers, maybe? How many requests can you handle with this approach?
So I measured the performance in comparison with Asynchronous server, and the numbers are pretty similar. Were pretty similar. And for example, boost context and boost coroutine, there is a library inside the boost coroutine based on boost context as well. Those libraries also contain some measurements related to switching. You know that switching is less cheaper than just like a normal function invocation, but it doesn't matter because usually you do asynchronous call here after switching, right? And asynchronous invocation involves, like, if you are dealing with a network, you need to use like epoll if you are developing in Linux, and epoll call, it's a syscall, and it requires much more ticks, like CPU ticks, to perform this. Thus, that overhead is very minimal, and usually you don't see any significant performance penalty. And using these techniques, you can create a very performant server application. And because actually for that purpose, for example, for network handling, it's a very cheap in comparison with another actions you have to do.
Okay, I have one question. I was also trying this boost context out and developed my own coroutines, and it looks so simple and nice. It's like you have a synchronous execution model, but then I thought about, well, wait, you have the stack and this is copied out. Did you have problems with outdated values or dangling pointers? Because you switch out, you find another thread, maybe the pointer you had is dangling sometime. Did you have this problem? How are you solving it?
Of course, you should carefully check the reference to stack, and you should avoid the situation when you resume your coroutine before suspension. You should avoid race conditions here, as I mentioned before. But if you correctly implement this, I don't see any reason to have a dangling pointers here and so such that. Okay, any questions? Okay, thank you very much for your attention.